This is problem number 33 for the practice exam 6, which covers chapter 22 and some of 25 mostly. Here you see with 33 and 34 both, these are NMR problems, and I wanted to start reviewing that for the final that's coming up very quickly. So several things here. This is a, let me uncover that one. This is a problem here where we have a molecular formula, not given or anything, but it's kind of implicit in the problem here. We have the same number of carbons, same number of oxygens and hydrogens, etc. And we have to try to figure out with the peaks here, what is what from this HNMR spectrum. So let's go through and review. With this particular one here, we need to know splitting patterns. And remember, I keep bringing this up here. We have 4 different criteria that I have pointed out there from the lecture. And it goes from the ease of deciphering from a spectrum to from the easy ones to the hard ones. So here we have number of signals is the first one, that equals the number of unique hydrogens, right? And then the second one here, we have the integration. Integration in this case is not given for problem number 33 here. It would be in the form of some kind of H's, the number of H's usually on an ACS exam, at least that's what they do. Number 3 here would be the chemical shift, and number 4 is the splitting patterns. And the splitting patterns in most cases boils down to the n+1 rule. And I'll show you how that's applied here in a minute. N is the number of hydrogens that's adjacent, in other words, next to the hydrogens that are giving off the signal. So right next to the signal hydrogens. In some complex cases here, the rule is n+1 times m+1, where m and n are 2 different types of adjacent hydrogens. Now, adjacent technically means usually within a 3 bond distance from each other. Okay, so first thing I'm going to look at with this problem here on 33 are the number of signals. Here we have a blown up signal that does occur on a lot of standardized tests where they want you to see every single peak that's in there so you can see the unique splitting. But here we have 1, 2, 3, 4 different types of signals. So here in the problem solving technique, you would go through here and try to determine the number of signals that would be given off by the hydrogens in each of the answer choices. 1, 2, 3, 4, so that's a possibility. 1, 2 here, but that methyl group is the same as this methyl group over here in the hydrogens. So B we can cross out. Okay, 1, 2, 3, 4 in this one. That one's a possibility. And 1, 2, 3, 4. And I'm just numbering this any which way here. Here we have 4 different types of signals here. Now, going way back here in the chapter here, a different signal is where we have a different magnetic environment. So they are unique hydrogens. So unique in the sense of how far they are from functional groups like this ester right here. And that applies to these other 3 choices here that haven't been marked out yet too. Okay, so we couldn't really do much with the number of signals. Unfortunately, sometimes you can determine a whole problem with that. No, in this case here, we have to go to both splitting patterns and the chemical shift there. Now, chemical shift here is something also to review. There's a table of numbers. It's very hard to memorize all the numbers you have to in organic chemistry, but the number one thing that I advise is not only memorization, but this kind of visualizing what's occurring. Draw yourself out a spectrum, a numbered spectrum like this on your blank sheet of paper after you've sat down and looked at the numbers long enough. And I'm going to run out of room here. And I'm going to put 12 way over here. There's not much in the 12 region. But okay, let's go through the functional groups. Alkanes are over here. Just plain old alkanes appear roughly around 1. That is usually an sp3 hydrogen. That's next to nothing. Okay, right here, if we have some kind of double bond here, let me draw the representative example here. Say we had something like this. Let me make that a 3. These hydrogens right here would appear roughly around 2 ppm. Oops, and this is ppm down here for the hydrogens. So any kind of double bond, that also does apply to a CC double bond, also roughly around 2 for the ones that are next to the double bond. This one right here, not these over here that are attached. Okay, and then we have this range here between 2 to 4 right here. There's lots of little tiny things that appear in there. For one, the triple bond will also appear in roughly around the 2 range also, really piling up right here. This particular hydrogen right here for the alkyne will appear at 2. And then we're going to have various hydrogens that are attached to something that has an X of some sort. Right here, an X, this hydrogen that's attached to a carbon that's attached to an X can be any kind of X, like a, let's see here, in the weaker sense, an iodide would be on the lower range, that would be this way. Whereas over here, if we have an oxygen, it's going to be closer to 4 ppm for that. So there's a number of things that are attached to X. Nitrogen here being a little bit less electronegative would be somewhere in the middle right here. We'd imagine a chlorine being somewhere over here as well with that. So basically you're looking at a periodic table and seeing where it is in the range here. So less electronegative things are over here by 2, and more electronegative things are over here by 4. Okay, and then we get over here to the 5-6 region, and then we have the hydrogens that are directly attached to alkenes. So these hydrogens right here, and that's caused by the anisotropy effect. Benzene's going to be a little bit higher. Hydrogens that are attached to benzene have more anisotropy, and that's, in other words, an induced magnetic field. And then if we have a hydrogen that's attached to a double bond directly, say like this one, but it has to be also attached to an oxygen here. That's the aldehyde peak right there that appears roughly around 9 or above most of the time. That's going to be some of the highest peaks right in there. Now what I couldn't fit on here, which is going in the 12 region, is something that's attached to a carboxylic acid. Sometimes, most of the time in practical chemistry, that doesn't show up. This hydrogen here is attached to an oxygen, so there could be a very broad peak there because of hydrogen exchange. So anyway, let's go back to this problem now. Problem number 33. And we see here, I always like to go to the peaks that have the highest chemical shift first. They are usually very informative. This one here that's attached to, this is something that's attached to an oxygen right here because it is at 4 ppm. All right, so going back to the table, that's this one. That's one that is highly important. If you have a carbon, and the carbon's attached to an oxygen right here, the hydrogens that are attached to that carbon will be around 4 ppm. Sometimes a little bit less, sometimes a little bit more. This depends on the uniqueness of that molecule. So that is our chemical shift, and we have to kind of simultaneously use splitting to do that. Okay, so here's our picture in our mind. Right now we have an oxygen and it's attached to a carbon, and the hydrogens here are connected to something. We don't know how many hydrogens actually there are right here until we see what it's connected to and how it's connected to it. So let's look at this signal. 4 ppm, and it is a triplet. Going down here, the n+1 rule is equal to then 2 + 1 because we have a triplet. Triplet means 3, and the peaks have split into 3, which means that the carbon that's next to it has 2 hydrogens. There are 2 H's here. This is what it then looks like. We can build the picture of this. There is a CH2 next to it. Okay. We go then back to our spectrum here, and we're going to look. We're going to look for what we have here so far. The oxygens here are here in this one. There we have a set of hydrogens. Here there's 2 hydrogens, and it's right next to something with 2 hydrogens. That means that's a very good possibility in A. Let's look down here at C. Whatever's attached to this oxygen right here is a singlet. This one here is not next to any hydrogens. That cannot be the answer choice. Then we can mark that one out. We can go to this one down here on D. You see that these are the set of hydrogens that are next to an oxygen, and it's right beside 3 hydrogens. So in this case, the n+1 rule would boil down to 3 + 1. That's a quartet. 4 signals there. So we have eliminated all the other answer choices already because it is not a quartet that's at 4 ppm. It's a triplet. So now let's identify all the peaks here just to finalize. We've selected the correct answer choice. It's A, but just to make sure and just so you guys have a good review of NMR here. Here we have a triplet. That's this one right here at 4 ppm. We go to the next peak at number 2 here. That is a singlet right here at 2 ppm. That's this one over here. The methyl group is not within a 3 bond distance from anything, and that is the correct chemical shift that I told you about here. If you have something connected to a double bond, it's usually around 2 ppm. So that's what we have here on that one. Here we have a big giant peak. 1, 2, 3, 4, 5, 6. That is the sextet right there, and that is where we have the n+1 rule is 5 + 1 = 6. Right there, easy math. And you can see that belongs to this one right in here, because it has 5 hydrogens that are next to it. This is one right here. These sets of hydrogens could have had complex splitting, in which case they could have been split twice on each side. Very rarely do you see that here on the ACS test or on your MCAT, PCAT, or whatever. That's fairly complex splitting. But in that case, the more complicated rule is this one here, right? That would be the mathematical formula. But this one, it was the simple rule. It boiled down to a sextet. But that is this one here. And then the last one, this is the furthest away from any kind of functional group because it has the lowest number, meaning it is the most shielded, not the most deshielded, but the most shielded. And it is the triplet. That is because triplet here, it is next to two hydrogens again, right over here. And again, that's the most similar to an alkane because it's the furthest from the functional group that is right here, this ester. And that's problem number 33.